Terrific. Okay, today we begin our
Rotational energy.
unit on torque. And torque
You want to give me a
is similar to work. Not that they sound the same, but they have a lot of similar things in it. Anyway, a torque is a force which causes a rotation. So anytime you apply a force on something that causes it to rotate, you are applying a torque. When you turn a doorknob, when you use a screwdriver, when you use a wrench, when you ride your bike,
crankshaft?
all of these are using torque. That's beautiful. Now, when we learned about work long ago in a land far, far away, work was equal to force times distance. And the force and the distance had to have what in common? They had to have the same direction. So the force and the distance both had to travel in the same direction. So if you were, say, pushing on your car because it was stalled, and you're out here pushing. Okay, so if you're pushing on your car, then you're pushing both down and forward, but since the direction of the car was forward, only this part of your force was actually doing work, right? So we had that force and we had that distance and they had to have the same direction. So all we cared about was this part of the force. The force and the direction and the distance had to have the same direction or it wasn't true work. Torque is also, that's the Greek letter tau, that's why it looks like a funny T. But torque is equal to force times distance also, but here the force and the distance act perpendicularly. So we generally stick a little perpendicular sign there. So unlike work, where force and distance had the same direction, here force and distance are going to have perpendicular direction. So let's pretend we have a bolt, and around this bolt we have a wrench. If I have a wrench on this bolt, I'm going to grab it over here on the handle and I'm going to push that direction. So this would be my force. And the distance is going to be measured from where I'm applying the force to where the rotation is occurring, the center of the rotation. So clearly this would rotate around the nut here. So that's going to be my distance. So notice how the force and the distance are perpendicular, and this is going to cause it to rotate. Now, if I want to get more torque out, but I don't want to use any more force, what do I need to do? Increase the distance. So the farther out I can reach, the more torque I could get. So if this wasn't strong enough to do this, and I was pushing as strong as I could do, what I'd want to do is stick something over the edge of this to make it longer, and then I could crank it from way over here. The longer that distance is, the more torque you're going to get, and eventually you're going to get it done. So that's the basics of torque, real simple, force times distance. They have to be perpendicular, but imagine there's a little hole here, and instead of me pushing or pulling on it, I just hang a weight there. Is that going to provide a torque?
Yes.
Yes, it's going to provide a torque. Is it going to provide a constant torque the whole time?
Yes.
Not necessarily.
Yes.
Now my hand, I'm going to grab it and I'm going to push and push and push, and it's going to be a nice constant torque. But why would this weight not be a constant torque?
It's going to the other side. Oh, it's not going to be perpendicular.
As the wrench turns, that's beautiful. Okay, we're just going to draw a really ugly wrench here. So as my wrench changes to here, the weight is still pulling down, but now am I getting the full amount of force I think I am?
No.
No. So what we're doing is we're saying, hey, look, my distance just got, even though I could say I'm having the same force, but now my distance got much shorter. So we'd have to take into consideration either how much shorter did the distance get or how much shorter did the force get, whichever way you like to say it in. Where would my torque disappear? Yeah, when it's straight up and down, when my wrench is going straight up and down and the weight is going this way, now I have zero distance because from the axis of rotation I've got nothing. So at this point I'm no longer torquing. I'm torquing the best when it's here. Not torquing.
You just saying it, I'm like,
I know. You guys are disturbed.
Yes.
Is there something that you've been on that deals with this constantly changing torque situation all the time?
Did I get the carnival?
Ferris wheel question?
The total world.
Pizza. Pizza. What? Cheese.
What is that?
Cherries. Cherries.
Bicycles.
Is that a bicycle?
Cherries.
That's a bicycle.
It's bicycle.
Okay.
Cherries.
Why are you buying a bicycle?
He's
It's been on.
Oh, it's the bit on.
Yeah, I heard that too.
I heard
it on.
Nice.
Anyway, in this section we have these
Your
things
cravings
called
are-
pedals.
That bike has a flat tire.
Pedals. What were they invented?
And this is you. Take your foot under
He has
the
long legs.
and you have really long arms.
I dislocated
Hi!
reach.
Okay. Anyway, when you're
That's like a Harley.
This is gonna be a nice video to read.
Yeah.
You were saying
clearly, I went to art school.
He wants us to understand the lessons.
It's just you. It's just me.
I need an actual bike.
Okay, so when you're standing on the pedal, you are pushing down with your weight. And which part of the pedal which part are you pushing down on, the front pedal or the back pedal?
The front.
You always push on the front pedal, you never push on the back pedal. The back pedal's just coming up. But have you ever, like, taken off on your bike and noticed the feeling is different depending on where the pedal is?
Yeah.
Yeah, you feel the strongest when your pedal is actually in this position. You like to take off when your pedal is up here because that gives you a bigger distance in the section where it's good. But realistically, the pedal from this position to this position, you're getting a lot of torque out as you're crossing through this section. Because at this point, this is where you're going to get the max torque. It's going to be where you're absolutely perpendicular. But above and below that, you're still getting some component of it. But once your pedal, gets down to here, you're getting no torque out of it. And the one in the back is just coming up to the top. And so if you grab it up on top and start pushing on here, again, you're pushing straight down. So it's not doing much either. It's only after you get here. And again, as you're sliding through this section, you're getting bigger and bigger and bigger. So here I have zero torque. And up here, I'm going to have my maximum torque. And then I'm going to go back to zero torque. And then the other pedal is going to be up in position to go through that cycle again. So the most torque we're getting is in this section. That's the part that you're really cranked down on it. And the other parts are just kind of coming up. That makes sense? Because you don't really change the angle of your foot. You shove in weird ways. It's pretty much just going straight down.
Actually, it depends on your gears.
Well, the gearing changes some other things. Yeah. And that provides a different type of torque back here because you've got different gears here. And as these are turning, you're turning this bigger thing, and so your distance is bigger. And so, yeah, actually it becomes a problem that way. If you have a little tiny car, and you put monster tires on it,
Down.
okay, your little tiny car has a little tiny engine in it. And so it can only generate so much power. But if it's generating power to the axle inside here, and you're trying to turn the wheel up here, how much force am I really going to get out of this? Not much, because again, the torque is that force times distance. When this distance is huge, then the F coming out is going to be small. So that's why in a small car we tend to have little tiny tires. And then in bigger vehicles that have bigger engines, we can put on bigger tires. So monster trucks, they need to have really big engine in there. And so one of the things that, has anybody ever been to a monster truck thing before?
Yes.
Yeah, the first time they came to Laredo, my kids were like, Dad, I want to go to a monster truck thing. And I'm like, I'm not raising rednecks. What are you talking about? But my kids really wanted to go, really wanted to go, really wanted to go. And it's like, okay, fine, the tickets weren't that bad. We're going to go see the monster truck thing. And we show up, and I'm walking around, and all the people that go to these all the time are there, and they've got all these like hearing protection devices or little things hanging around their neck that are earplugs that are going in. It's like, why is everybody wearing earplugs? And then we go into the LEA where you're in this nice enclosed thing, and you've got these monster trucks, and none of them have a muffler at all, because that muffler takes a lot of power away. And these guys need to get maximum power out, and so the muffler is gone. And I didn't know this, so we spent the whole time doing this because it was incredibly loud in there. So we didn't know. But it was actually a lot more fun than I thought it was going to be. It's really impressive to watch a car go from 0 to in like this distance. Paramount trajectory.
He's like physics.
Yeah. I actually enjoyed it much more than I thought I would. So,
You gotta get the time down.
have you also noticed? How many of you guys have noticed that little cars that have little tires have 4 lug nuts? And then you get slightly bigger tires, and you get 5, and then you get to bigger ones, and you go like up to 7. And yeah, why do you need more lug nuts with these bigger tires? And again, it's because your engine can generate so much torque that you can actually rip those bolts right off, and you can shear it because of the amount of torque it produces. So if you only had 4 bolts, it'd be on a big thing, it would rip them right off. But you can get away with only 4 bolts on a little tiny one because it doesn't generate that much torque where it's going to hurt it. So you put in a monster engine into your little vehicle, and you may have problems here. Yeah. Okay. So these are just like some super general ideas of what torque is. Kind of making sense. So you can see how an angle would play into this in certain situations. And we'll get into that a little bit later, but for now we're just saying that that's there. So most of the time we think of torque as being in that total perpendicular part. And so today what we're going to do is we are going to talk about equilibrium. And you're saying we've talked about equilibrium before. And you're right. What does equilibrium mean?
Restoring force.
Equilibrium just means balance.
Oh yeah.
Joseph has a question.
So like silly question, but like legit question. What if you were to like get a really big engine, but you had like a truck like really tiny tires? Like what would happen?
Yeah, you would be able to go up really steep hills. And that's the problem with a little car. If you have a little car with a little engine and you put big wheels on it, as soon as you hit a hill of any appreciable size, you're not going to have enough torque to get up the hill. Whereas if you have the opposite problem, if you have the big engine and you put tiny tires on it, you're going to get lots of torque, but it's wasted torque because the bigger the wheel is, 1 revolution means I go a farther distance. And so I want to be able to go fast like that. And so you would basically go really slow, but you'd be really powerful. You could carry huge weights or drag, tow huge weights with that, but you'd go very slow. Okay, equilibrium again means balance. And normally we were talking about balance of forces and things like that when we talked about equilibrium, when we talked about statics. But now we're going to talk about equilibrium of torques. And so equilibrium again just means balance. So equilibrium of torques means our torques are equal in all directions. So again, since a torque causes a rotation, what's gonna happen is, if I hang some weights on a little balance like this, then I have the weight on the right is trying to make everything go clockwise, and the weight on the left is trying to make everything go counterclockwise. Where's my pivot point? Yeah, the pivot point's right here where it's connected. So I have a certain distance over here, and I have another distance over here. We always measure our distances from the pivot point. So if this is like a 3, and this is a 5, and this is a 3, then that's going to be a 5. This make sense? Because, yeah, again, the torque is equal to the perpendicular force times the distance, and we say, hey, the force is caused by the weight here. So the weight's pulling me down, and the distance is 5, so I have 3 times 5 is going to equal 3 times what? Hey, 5! So that's why this one is 5. And that would balance them out. Because this one on this side is trying to get it to torque counterclockwise, and this one's trying to get it to torque clockwise, and they're going to balance out. Easy peasy. Let's make it more complicated.
Yay.
Yay! What if,
Today's Friday.
hey, today is Friday.
Wow. And we're starting a new lesson so I can forget it on the weekends.
Okay, so we'll go back to what we just had a minute ago, but we're going to add some things.
Which was Monday you said forget. No, I just wanted to. Oh no. Oh, we got this.
I don't think
It'll be
I'm
easy.
space. Like,
Okay, we might as well just take a picture.
So I'll give you a moment to write this down. Okay, so those numbers are the ratio of the sides. It doesn't really matter what the actual size is. All that matters is the ratio between them.
That one's fine, obviously.
And so we'll just label these so that they all have a little name. No! We're not using our imaginations at all today. That hurt.
I'm not a big fault.
I imagine you guys are good students.
Oh.
Are we supposed to have it?
Okay, everybody ready?
Yes.
What?
That's the way I think it is.
Okay, so again, 3 times 5 equals 3 times 5, so it's going to be 5. That's super duper easy, right?
Yes.
Now, how hard are we pulling on this string? I'm going to just add the masses. So 3 and 5 make 8. So that's going to pull a total of 8. So then I say, hey, 8 times 3 must equal 2 times C.
12.
Am I right? So C is going to equal 12. Because 8 times 3 is 24. Divided by 2 is 12. So then I say to myself, hey, 12 and 8 add up to 20. So that must be 20. Kind of amazing so far. This is working out this nice problem. But okay, so 20 times 4 divided by 5 is going to equal
Open 25. What is that?
20 times 4
Oh!
divided by
I
5
heard
is
20 plus 16. 16. Yeah, bro.
going to be equal to 16.
And here's where our beautiful whole numbers are going to go away. Now, going up, we had it pretty easy, right?
That means the total mass that we're pulling up with is
Total 80
20 plus 16 is going to equal
6.
this will come in handy later. So we're just showing you that right now. Now, on the way back down is a little bit trickier than it was on the way up. On the way up, it was super easy.
Oh,
This
I know.
times this equals that times that. I've got to make. Now, if I'm going down, I know that the total of E plus this line over here has to add up to 16. Now, which side's going to be heavier, the left side or the right side?
Left.
They're going to be equal. If I want them to be equal, then the right side has to be heavier because the distance is smaller. So again, the torque is going to be, if I have a smaller d, I need a bigger F. And over here I have a bigger d, so I need a smaller F. Right? Okay, so over here I'm going to have, to the right, I'm going to have the bigger force. And so how much force do I need over here? Well, what's the total distance?
6.
The total distance
Oh,
is
5.
5. So I want 3/5 of it over here, and I want 2/5 of it over here. That make sense? So I need the bigger chunk on the smaller distance and the smaller chunk on the bigger distance to keep them balanced. So now we actually make
Calculator.
so 3/5
3 and 8.
of 16, 9.6. And over here we get 6.4. Are you with me?
Not on the way down.
Not on the way down. So we get to the next line, and the next line has how many total pieces?
4.
4. Now, so over here we know we're going to have 4 at the bottom, but this is the small side, so I need the biggest chunk. So I need 3/4 of it over here, and I need 1/4 of it over here. A piece? So this is going to be 1.6 on this side. And T is going to be 4.8. And now we look at the bottom one and we say, hey, F and G, their stick is a total length of 5. So who gets the bigger chunk? F is going to get the bigger chunk, so it's going to get 4/5, and G is going to get 1/5 of the 1.6. So we're going to get 0.32 over here, and we're going to get 1.2 over here. Now, is there a way to double check that this probably is correct? If we add up A and B and C and D, I can line up this in between, and E and F and G, this should, looks like it's in a completely different column. What should these add up to?
36.
They should add up to 36, what we said the total mass should be. So if we add these up, what do you get? I got 36!
Wow.
There's no way.
Okay, so that's a good way of just double checking and saying, hey, this makes sense, that should work out nicely. Okay, so that's gonna be the easy side of today's assignment. It's gonna work just like that. The tricky part is gonna be what happens if, what was the thing that's not very believable about the way we drew this?
We are all get a balance.
Like all the
How
circles
it's
look
angled.
exactly the same.
How is that equilibrium? How it's distributed.
Our little sticks that are horizontal,
Oh, they wait.
they apparently are massless. Okay, now I can see the little strings. If I'm hanging weights with a string, I can make the string so small that it's insignificant, right? But the little stick that it's on is probably going to have an appreciable mass because it has to carry all those other masses. So what happens if the sticks have mass? It throws everything off. It's not as bad as you think. On the way up. On the way down, I'm going to let you think about that. But on the way up, okay, let's say we have a stick here, and this stick, we'll make the stick nice and small. So we're going to have a stick of 1. If the stick has a mass of 1, then 5 is no longer B. Now, if the stick has a mass of 1, that's what we do is we pretend that the stick has an extra little mass. But where are we going to put that mass? In the center. So if this is 5 plus 3, this is a total distance of 8. So the midpoint would be at 4. So the midpoint would be right here at 4. So it would be like having an extra weight of 1 hanging at 4. So you say, hey, that's really hanging 1 over from where this is, right? From my pivot point. So now I'm saying, hey, I have 3 times 5 plus I have 1 times 1 that are trying to torque me counterclockwise here. And so now B has to equal 3 times whatever B is going to be. This making sense? So now I'm going to have 8 plus 1 is going to be 3x. So I'm thinking x must be 3. Does that make sense? No, it doesn't
No,
make
it doesn't
sense
make
because
sense.
I added 3 times 5. I was going to say that looks wrong
Yeah.
mathematically in my head. Oh, bad when you're taking drugs. 15 plus 1.
There you go.
So that's going to be 16 equals 3x. So x is going to equal a much more realistic number. Why did we say 16? 5.3. So 3 had to get bigger.
Back to algebra.
So now, again, now you have to add up the 3 plus 1 plus 5.33 becomes this number, and so on the way up. That make sense? On the way down, it's going to be a little trickier because it's not going to just be a straight work out these fractions because there's another fraction to go in there and you're going to have to figure it out. The algebra is a little bit more complicated, but I'm confident that you guys are smart enough to figure this out without help. Because it's better for your brains if you're not just watching me do it, but if you're figuring things
You
out.
have too much
So,
figures.